Alright, we're going to get started today. We're going to do a little division, and then I'd like to talk some Newton's laws just to clear things up when I was looking at your quizzes. You still have another day to get your quizzes in, so, and then even if you need more time than that, honestly, it's pretty much getting them by the end of the month now. So let's talk some division here with square roots. Yesterday we did multiplication properties. This is your division property. However, we've already seen this. You've already taken notes on this. We know that the square root of a over b is going to be equal to the square root of a divided by the square root of b. And that's your division property. This is going to hold true as long as a is positive and b is positive, or 0, because you can't take negative square roots. So if you had something like, we want to put numbers into it, I can simplify the square root of 8 over 2 as the square root of 8 over the square root of 2, which, as we know from yesterday, you can actually simplify the square root of 8. Just looking at your denominator or your numerator right now, you can actually simplify the square root of 8 by saying, hey, the square root of 8 is actually the square root of 4 times 2. And then our denominator we didn't touch, which would be 2. And that's going to equal, again, you can pull this apart, the square root of 4 times the square root of 2, all divided by the square root of 2. You should note that these will cancel now. Square root of 2 divided by the square root of 2 is 1, and that leaves you with this. We'll just put one line, a couple lines through it so you can see it. And that's going to leave you with the square root of 4, which equals 2. And then if you did like order of operation wise, you'll see that the square root of 8 over 2 is equal to 8 divided by 2 is what? 4. So that's the square root of 4, which equals 2. So I mean, either way you get the same answer. It's just that this way here gives us more options along the path to do something different, and also sadly probably make a mistake. But sometimes it's not going to be as easy as just, hey, I can divide the inside of that to get it. But we looked at this before. Let's get another example in here. Let's see if the book has something nice here. Actually, it's got something good. So here's another example of this. We can take square root of 11 over 49. Here, again, you can break it off into the square root of 11 over the square root of 49. And you know the square root of 49 is 7 because it's a perfect square, so you can go ahead and solve that. And then the square root of 11, you can sit there and see if you can break that apart, but probably not. It's not really divisible by anything, so it's looking like that's as simplified as we can get for that example. Right, so this here would be your answer to that. This is an 11. Be cooperative today. Right, we can also look at ones where it has variables in it. If you recall your variable stuff from yesterday, was this 25 over b to the 4th. In this case, again, same kind of thing. You can break it off into the square root of the numerator and the square root of the denominator. So we're going to say this is the square root of 25 over the square root of b to the 4th. And these are both perfect squares. I know the variable one is because it is an even number, if you recall from yesterday. If you have even numbered exponents to variables, they are perfect squares. So here this is going to be 5, and over here is going to be b to the 2nd. You just have your exponent. So this will be 5b to the 2nd. Not too difficult of a property. It's just saying that you can break up your fraction within your square root. The other way that your book's going to tell you how to do it 2 other ways. We're going to, how do they call it here? Simplifying radicals by division. So here we're going to get into simplify by division and simplify by rationalizing the denominator, which actually really isn't too difficult. It's just kind of a strange thing that we ask you to do, and it's like one step further. It makes things look nicer, but a lot of times it's not necessarily necessary for whatever you're trying to solve. So let's look at simplifying things by division. So here we got simplify by division. I don't know if I have a good example on here or not. No, I have rationalizing on there. Simplify, I guess we can do one from the book. And here's your example. We get the square root of 88 over 11. In this case, it's going to ask you to do the division in here first. So 88 divided by 11 should be giving you the square root of 8. And then once you get out of the fraction, it's like we did yesterday. You want to simplify this by looking for common factors that are perfect squares. So we know the square root of 8 is going to be 2 square roots of 2, but let's get there the long way, I guess. That's going to be the square root of 4 times 2, which is going to equal the square root of 4 times the square root of 2 due to yesterday's property, which is going to equal, and we can solve the square root of 4 as 2 square roots of 2. So there's your answer to that one. Sometimes you also get this with variables as well, but we know how to do division with variables from a while ago. So here we got 12a to the third divided by 27a. And you can probably start thinking right away that, hey, I can't really divide this, but you can reduce this fraction. Right? We can divide out within the fraction. I can divide what can I divide? I can divide a 3 out of each of them, and I can divide an a out of each of them. So I can divide each by 3a. And again, this is just reducing your fraction, so I'm actually dividing it by 1, which doesn't change the value here. So this is actually going to equal, and I didn't touch the radical yet, 12a to the third divided by 3a. 12 divided by 3, get your numbers down first, is 4. A to the third divided by a knocks off one of your exponents, so that's a to the second. And that's going to be divided by 3 divided by 27 gives you 9, and a divided by a gives you 1, which is nothing. So this actually reduces down to 4a squared over 9. And all what I did there was divide out a factor from both of them. So that's the same thing as saying, hey, 3/9, I can divide this by 3 and I can divide this by 3, and I get 1/3. It's the same thing. I'm just reducing that fraction. It just has a variable in it. So that variable is a factor that I can factor out of it, so to speak. Once you get to this point here, you'll notice that 9 is a perfect square, so we might as well break it up. And you can get the square root of 9 on top and the square root of 4a squared. 4a squared is also a perfect square due to the fact that 4 is a perfect square and a squared is a perfect square. So we know that the square root of 4 times the square root of a squared over the square root of 9. And again, you can start simplifying these whenever you really wanted to. But we can solve each of these. So the square root of 4 is 2. That's going to be times, I'm not going to use a dot, times the square root of a squared. Remember, those cancel, so that becomes 2a. And the square root of 9 is 3. So it all reduces down to this, which is a lot nicer to deal with than this. Let's see if there's another example like that, because that is a little tricky with the different variables you get thrown in there. So let's look at another example of that. Let's see, the book has square root of 90 over 5. Right? So looking at this, you should note that you can reduce that fraction. So that's what I'm going to do first. I'm going to reduce the fraction. This one doesn't have variables, but I'm going to divide this by 5 and divide this by 5. That's actually going to get rid of my denominator because my denominator is going to become 1, and the square root of 1 is just going to be 1. And 90 divided by 5 gives you, I don't know, what is that? 18. That gives you 18. So this is going to turn out to be just the square root of 18 over the square root of 1, which turns out to be the square root of 18 over 1, which turns out to just be the square root of 18, which you can then reduce because I can tell you right now the square root of 18 is equal to the square root of 9 times 2. So I know we have a perfect square in there, so I'm going to divide it by that perfect square. That's going to equal the square root of 9 times the square root of 2. And I can solve the square root of 9, which is 3, and I can't do anything with the square root of 2, so I just tack it on. So you get that answer. So it does reduce it down, gets rid of the fraction. This looks a lot cleaner and a lot nicer, and it is preferred. I guess it really depends on what you're doing, but if you're ending everything, that's a great place to end. So again, pretty much same thing as what this little postulate says, just reduce the fraction in there beforehand. Actually, let's look at another one with a variable, see if we can get a variable here. Example, let's do square root of 27x to the third over 3x. This one does have a variable, and you'll note that you can reduce this. 27 and 3 share a common factor of 3. I guess we're doing a lot of 3's today. So I can divide each by 3, and then x to the third and x share a common factor of x, so I'm going to divide it by 3x. And I'm just reducing that fraction, that's all that's happening. 27 divided by 3 gives me 9x squared because we're taking away one of the x's. Over here it gives you just 1. So this is going to equal the square root of 9x squared over 1, which equals, again, you can pull that apart if you're more comfortable doing it that way, or you can just write the 3x out there if you want to do it in your head, but that's going to be times x squared. And then over 1, it's not going to matter, so this is going to equal square root of 9 is 3, and square root of x squared is x. So this turns out to be just 3x. Any questions on where anything came from so far? It's pretty straightforward. Reduce the fraction the best you can, and then use this property to reduce it any further, if you can. If you can't, then it's going to come to this step here, which is rationalizing the denominator. You do 31 on the page when you're done. Yeah, I don't know what does 31 say about this? Yeah, we can do 31. I can do 31 real quick right now. 31's not too difficult because you got that perfect square as a denominator. Hopefully you know your 11's tables, but looking at 31, you get the square root of 120 over 121. Right, you know right away this 121, that's 11 times 11, right? So that's a perfect square for 11. So let's go ahead and pull it apart and deal with that. So this is going to be the square root of 121, which again is going to turn out to be 11. And this will be the square root of 120, which equals the square root of 120 over 11. And now we got to break up the 120 here. That you're going to sit there and think about factors that are perfect squares. I don't know any off the top of my head right now. So I'm going to sit here and just start dividing it by things that might be perfect squares. I know 4 is going to work, but it might. Let me try 120 divided by 64. Okay, I know 4 is going to work. So I know there's a square root of 4 in there times, radical went too far, times the square root. I guess I want to put that, I want to put it more. So 4 times what is 120? 120 divided by 4 gives you 30. 30, don't forget your denominator's still there. So 4 times the square root of 30, so this is going to become the square root of 4 times the square root of 30 all over 11. That becomes 2 square roots of 30. I don't know if 30 can be broken up more or not. I'm going to have to sit there and look at that. I don't think it can, so you're done. Four doesn't work, 9 doesn't work, 16 doesn't work, 25 doesn't work. Yeah, you're done. Hardest part was probably figuring out the 4 that goes into that. But that would be 31. And we are okay with this because when it comes to rationalizing the denominator, we don't want a radical on the denominator. That's the whole point of the next thing we're going to do. So when it comes to rationalizing the denominator, so we want to rationalize the denominator. This whole thing is we don't want a radical in the denominator. That's the whole point of this. We don't want that. We want to get rid of them. So sometimes when you do all of this work, you still get a radical inside the denominator, and we want to get rid of it. And it's actually pretty simple to do. You're just going to pretty much multiply through by that denominator. Let's get an example going here so you can see what happens. So maybe in the end your answer gets to be 2 over the square root of 5. Right? 2 is as simplified as it can get. I mean, it's just one number. And the square root of 5 is as simple as it can get without being your rational number and actually solving it out. But the problem here is we don't like having radicals in the denominator. So we need to get the radical out of the denominator. And it's really simple to do. You're just going to find an equivalent fraction to this where your denominator is not under the radical. In order to do that, you just multiply the top. So we're going to multiply the top and the bottom by the square root of 5. In doing so, your top is going to be 2 times the square root of 5 because you can't do anything there. And your bottom is going to be the square root of 5 times 5, which again, I'm doing this the long way. If you want to realize this is going to be the square root of 25. And this will be 2 over the square root of 5. And then you can actually solve the square root of 25, and this would be 2 over 5. This here is preferred to this. This is a better answer than this, even though this one looks a little bit more complicated. But the fact that we don't have a radical in the denominator is better than having one. So we want to get rid of it. And that's just called rationalizing the denominator. You're just basically going to multiply the denominator by its square root. Let's get another example. And again, you want to make it so it's a perfect square on the bottom. So it's not actually going to be the same thing all the time, like this one here. We'll do this one. So this is square root of 7 over square root of 8n. So first off, this here is not simplified, and that's why it's not going to be nice. I can simplify this more. I can take the square root of 8 and write it as 2 square roots of 2, which we've done like 3 times already this lesson. But let's look at it. Do we want to do it that way? Yeah, we can simplify that out. Let's simplify that out and see what happens. So we're going to simplify out the denominator. The numerator we can't do anything with, so that's going to be remaining the square root of 7. Denominator, again, that's the square root of 8 times n. So that's going to become 2 square roots of 2 times the square root of n. And this is going to stay the same. Again, if you didn't follow that, square root of 8 times the square root of n, this becomes the square root of 4 times 2, which becomes the square root of 4 times the square root of 2, which becomes 2 square roots of 2. And then you're multiplying it by the square root of n as well, times the square root of n, which means I can combine those square roots going in reverse of what we did yesterday. So it's going to be it's going to look like the square root of 7 over 2 square roots of 2n. And once you get it simplified down, it's going to be multiplying by the square root of 2n. Yeah, by the square root of 2n. Right. In that case, the square root's going to go away on the denominator. So you're going to get 2 times 2n, which I mean you can do as 4n, and this will be the square root of 7 times 2 times n. 7 times 2 is 14n. And then you can simplify this even further by doing the 2 times 2. So this is going to equal the square root of 14n over 4n. And then you got to think to yourself, can you reduce the 14n anymore? 4 is not going to work. 9's not going to work. So this reduces down to this. And again, that's rationalizing the denominator. You want to multiply the top and bottom by the square root you got here to make it nicer. But make sure your numerator and denominator are simplified as best they can before you start doing that. We can get another example of that because that's a little strange. Let's get another example. Let's do, what do we got here? 3 over the square root of 3. In this case, each of them are already as simple as they can get. So you're just going to multiply by the square root of 3 on both sides. So this is going to become 3 square roots of 3. And over here is just going to become the square root of 9. Or I guess I'll write out each of this. I mean, it's going to be 3 the whole in the long run. That's what you're going to look at and be like, it's just going to be 3 and not do any of the steps. But we'll look at the steps in between. This will be 3 times 3, which equals 3 square roots of 3 over the square root of 9, which equals 3 square roots of 3 over 3. I mean, the whole reason was to get rid of this radical, and that's what happens. Then you look at yourself, can you reduce the top at all? Which it does not look like you can. No, but what you can do though is 3 divided by 3 is 1. So these will actually cancel and you'll be left with just the square root of 3. So don't forget your little division things there. Rationalizing the denominator just takes a little getting used to. So let's look at square root of 5 over square root of 18t. Okay, so in this case, square root of 5 you can't reduce or simplify anymore, but 18t you can because of that 18. So we know that we can break that up into square root of 5 over square root of 18 times the square root of t. I'm not going to touch the square root of t because I can't do anything with it. I'm not going to touch the square root of 5 because I can't do anything with it. But I can break up the square root of 18 is actually the square root of 9 times 2, which is the square root of 9 times the square root of 2, which is 3 square roots of 2. So what I'm going to do is I'm going to rewrite it all as the square root of 5 over 3 square roots of 2 times the square root of t, so it's going to be square root of t because that's under the radical as well. In that case, I'm going to multiply each side by 2t. And here I'm going to get 2t square roots of 5. And on the bottom, I'm going to get 3 times 2t. Because again, I'm sorry, that's under the radical. My mistake. That's under the radical because when we multiply by these, radicals are going to cancel out and leave you with just 2t. So this is going to be 3 times 2t, which is going to be 6t. Again, you don't have to do every little step like I'm doing. I'm just trying to show you where everything's coming from. And over here, you're going to get the square root of 5 times 2 times t, which is going to be the square root of 10t over 6t. And then you're going to think if you can reduce any of this anymore. 10t does not work with 4 and does not work with 9, so that's where you're going to be ending. So that's your answer. Any questions on any of it? Your assignment is actually continuing with things. It is page 582, 28 through 43. They're kind of fun. Just kind of hardest part is probably figuring out factors that are perfect squares. But if you guys need me to do any other examples or anything, let me know. Because I do want to take at least 5 minutes here and talk about Newton's laws. I was going over the quizzes, which you still got time to do, but I want to clear some things up on Newton's laws that wasn't very clear, I guess, the first time around. Okay, we're going to clear off math here and let's look at some science. Let's go through Newton's laws real quick. Newton's laws. So Newton has his first law, which is the law of inertia. That's not how you spell inertia. Inertia. Biggest thing when it comes to the law of inertia is do not forget the constant velocity aspect of it. So the law of inertia states that if an object at rest, I'm sorry, we'll just say an object at rest. An object at rest will stay at rest unless an outside force acts on it. In other words, I don't know, someone in their quiz uses the laundry example. I thought that was great. The laundry on your floor is going to stay on your floor until you pick it up, or something else forces it to move, like the wind or some other thing, right? This is one part of it. This is only one part. This is the first part, I guess. Well, it really doesn't matter. This is one part of it. The other part deals with objects already in motion. So it's going to be very similar to this, but this says an object moving at a constant velocity will remain moving at a constant velocity unless an outside force acts on it. So here, if something is moving at a constant velocity, meaning it's not accelerating, so it's not speeding up, it's not slowing down, and it's not changing direction, you need an outside force to either speed it up, slow it down, or change its direction to accelerate it. If not, it will continue going in that path, that straight line path, indefinitely. It will never stop unless an outside force acts on it. So if we have a net force of 0, that means two things. Well, it really only means one thing, but it means two things, one for this and one for this, right? I could have a box that has, hey, I'm forcing it in this direction and this direction of 10 newtons and 10 newtons. They will cancel out. It will stay at rest. It's not going anywhere. The only way I need to do this is if I add like another force over here of something, then it will start moving. That's because Newton's first law, object at rest. But, I guess I'll leave that over here. Also a net force of 0. If my object, my box, is already in motion, if it is moving at a velocity, let's say your velocity here is, I don't know, 10 meters per second squared. It's moving at a velocity of 10 meters per second squared. It will stay moving at this velocity indefinitely until an outside force acts on it. That's still Newton's first law. So net force, if you have a net force equal to 0, this really means there is no acceleration. And that's going to come in light in Newton's second law as well. So let's look at Newton's second law here. Newton's second law is force equals mass times acceleration. You can name it that all you want. This is really what it is. It's this formula, right? So if we have a net force of 0, so force here equals 0 because our net force is 0, our acceleration has to also be 0. That's Newton's first law saying that. And that makes sense because you can't have an object without mass. That's just kind of the definition of matter. Matter is something that has mass and takes up space. You cannot have something that doesn't take up space in order to exert a force on it. You'll have an energy. The energy is the only thing out there that doesn't have mass, and you can't exert a force on energy. You can't push or pull light. It doesn't work that way. So if force is going to be 0, one of these, because of your 0 product rule, if you remember in math, one of these has to be 0, and mass cannot be 0. So it has to be acceleration. So acceleration would have to equal 0 there. In mass, it doesn't really matter. It doesn't matter how big your object is, it's still going to apply to Newton's first law. It doesn't matter how big your object is, it'll still apply to Newton's second law. So there's that. Newton's second law is a little bit more in depth when you come to context as well. So I'd like to talk about that a bit. But basically it's saying that the more mass you have, the more force is needed to accelerate it. Or any version of that. I mean, you can be like, hey, if this thing is accelerating faster, if we want these, right, then we need to put more of a force on it if the mass is the same. To make it accelerate faster, you need to push it harder. Or if you're comparing masses, the thing that has the larger mass compared to the smaller mass, if you want to apply the same force to it, the larger mass is going to have a small acceleration, while the small mass will have a large acceleration. And this is how this goes into your Newton's third law, which is your action-reaction forces law. and a lot of you did pretty good on that one, actually. A lot of you wrote it how I liked you to write it as well. I didn't take off if you wrote it the other way, but Newton's third law states that if object A exerts a force on object B, then object B will exert a force on object A that is equal in strength and opposite in direction. And you experience this every time you touch something. Like if you want to push against a wall, I have my wall here. I am going to stand here, and I am going to push on this wall with all my might. This wall is also going to push back on me. In fact, you can probably see it if you ever did like a push-up on the floor. You push down on the floor pushes back on you. It actually accelerates you upwards, not because its force is stronger, but because your mass is less, right? The forces are equal, so that's where this thing came into play. If my forces are equal and my mass is small, then I better have a large acceleration versus a large mass. I have a small acceleration. Think about your rocket coming off of the Earth, right? It's going to force a rocket on Earth, and then the Earth is going to put a force of Earth on the rocket. These forces are the same strength. So if the rocket pushes down with 10 newtons, the Earth is going to push up with 10 newtons. The forces are the same. Acceleration is going to be different because the mass is different. Earth has a large mass, so it's going to have a very small acceleration. You're not even going to notice the Earth accelerating. However, the rocket has a small mass, and therefore, in order to make up for the force, it's going to have a large acceleration. The other thing that a lot of people did actually really well on was why these forces don't balance out. Why aren't these balanced forces? And that's because this is a force of Earth on the rocket, and this is the force of the rocket on the Earth. If I can finish my words. They are acting on different objects, so it does go in different directions. Objects are different. Right here you'll have a wall and a person. For Newton's third law, you do need two objects. Anytime two objects are interacting, they're doing Newton's third law. So hopefully that clears up a little bit. I mean, overall you guys didn't do too bad on the quizzes, but there were some just common mistakes and common misconceptions that were there. So if you guys have any questions about anything, feel free to email me. We are going to end it. Science, the rest of science is available, I believe. Enjoy making your Rube Goldberg machine. They're kind of fun. And I guess I will talk to you tomorrow. So long. Goodbye.